Hi, today we're going to continue our discussion from the last lesson. We're going to look at acids and bases in a little bit more depth. Hopefully we're going to open up your field of view just a little bit. Before I get started, of course, I always forget to do this before I hit go. I'm going to switch to a better color. Just as a brief warm-up before we get started, remembering what you remembered about last lesson, you should be able to look at these substances, take a minute, and identify each of these as either an acid or a base or none of the above. So take a minute, do that. You can hit the pause button if you like. But I'm going to get started. HBr, it is not on the list. However, knowing what I know about bromine is found in group 17. Don't forget fluorine, chlorine, bromine, and iodine. So if I were to put H's in front of them and bond them with hydrogens, these substances should all display very similar properties. That's what, of course, being in group 17 means. So if HCl is found on table K as an acid, then HBr, it would stand to reason, is also an acid. SiH4, well, if we're going to play that same game, Si, silicon, is found right below carbon, and I know that CH4 is neither acid nor base. That H bond there, that's not quite polar enough to get pulled apart by water, so I'm going to say none of the above. You might think that there's an OH in this substance. This is not a base. This is actually rubbing alcohol, the chemical formula for rubbing alcohol. It's not on your table, and it's not chemically similar to anything found on the table. However, the last option, barium hydroxide, does look suspiciously like calcium hydroxide, strontium hydroxide, so this is going to be our base. So let's take this idea and move on. What I kind of want to put the idea in your head is that even though the Regents isn't really going to expect you to notice any acids or bases beyond what's on the table, we can apply our knowledge of chemistry and our knowledge of the periodic table to kind of expand into identifying a substance that you may never have seen before into a category and maybe guessing some of its properties. That being said, we should talk about table L because I have a confession to make. When I showed you table L on the last slide, on the last presentation, it only had 3 rows, 3 compounds shown, and there's definitely a 4th one. I copied the full picture this time, and it's ammonia. But if you look at the formula, it's depending on how you want to. I mean, it almost looks like CH4. It's not CH4, obviously. It's next to, right? Not above and below, and that's not how the periodic table works. But, I mean, looking at it, it's just NH3, nitrogen and hydrogens. That's got to be like an acid, because there's only H's. But then if you look on any source looking at the pH scale, ammonia's pH, depending on the solution concentration, is basic. It's definitely a base. I should mention here this word alkalinity. So acidity is how, like, being an acid. Alkaline is the opposite. Basic and alkaline, they mean the same thing. I'm losing the thread here. That's not the point we're trying to make. The point we're trying to make is NH3 is a base. How is NH3 a base? When there are no oxygens, much less hydroxides. We saw that based on our Arrhenius definition is that acids, I was on a roll for a second. Let's clean that up. That was bad. Acids create either H plus or H3O plus in solution as the only cation, and bases create hydroxide. Period. The end. So where's the hydroxide? I mean, either NH3 isn't a base and the reference table is wrong, or the Arrhenius definition is narrow. So to understand how NH3 acts as a base, ammonia acts as a base, I want to, instead of looking at what the products are, I want to kind of look at the products and the reactants. I want to look at the chemistry, because I think that a way of understanding how acids are acids is less in what they do and more in how they behave, if that makes any sense. So how does HCl interact with water as it dissolves? Well, HCl, aqueous, we know it becomes H plus and Cl minus, aqueous. But we kind of said something before. I said something and I just said to like go with it. Well, now let's not go with it. I said that H plus in water isn't really H plus. And really it's better to say that it's H3O plus. And I actually want to think about it that way. So instead of saying H plus aqueous, I instead want to kind of like think about it in saying that I guess it would be, one way of looking at this would be to say that HCl gives an H plus to water to make H3O plus. And this should make a little bit of sense if we consider the Lewis dot structure for water, and then we have an H plus floating around. Keep in mind that an H plus is basically a proton. And actually, I haven't mentioned this before. The word proton really ties into acid base. Since H plus ions are just protons, the two are kind of used, they're used interchangeably. The word protonation or deprotonation can be used to signify the gain or loss of an H plus ion, specifically ion, respectfully. So the water is protonated by the HCl, and the HCl is deprotonated by the water, if you want to think about it that way. But this works out kind of nicely in that this lone pair of electrons can be used to make a covalent bond with the hydrogen ion, and it makes a structure that looks like this. And this whole thing, remember what polyatomic ions look like, it's they're covalently bonded with a charge. This is what the hydronium ion looks like. So this is why I said in water, H plus isn't really H plus. That proton has so much charge and is so tiny, that concentration of charge is relatively unstable, and it's going to latch on to any electrons it can find, because being in that bond is a little bit more stable and a little bit more desirable overall. I mean, it's not doing it, it's just, it happens because it's more stable. I would say that something similar could happen here. That when sodium hydroxide can interact with water, that we're going to get something happening. Now here's the thing. It's a little bit misleading, but I'm going to tell you what happens. We're going to get this plus, I should write this in the right order. Delete that. We're going to make our sodium ion like we expect. We're going to make some water, and we're going to make some hydroxide. So if we're going to think about this in a similar way, HCl gives an H plus. Well, the sodium hydroxide is a base, so it's not going to do what the acid does, and it's not going to give an O, and it's not going to give an H, because, like I said, it's not an acid. If anything, I think what's going to happen is it's going to take to really make this make sense. And so what I'm kind of saying is that this hydroxide becomes this water, but keep in mind that when you have a chemical reaction and you have the same substance, shown on, whoa, I want that. There we go. I did not expect that to happen. When you have the same substance shown on both sides of a chemical equation, go back, draw a line. The buttons are disagreeing with me today. We can omit any chemicals that are unchanged by the reaction, so we end up with the same exact reaction we saw before. So thinking about this theory in the other direction as a base with sodium hydroxide doesn't actually make a lot of sense. What we're going to do instead is attempt to pen, bring back, go over to blue. If I tap, does it go away? It does. I want to think about ammonia. Ammonia will interact with water and if it's going to be a base, we can't treat it like it's an acid. So here's the thing I want to show you though. Keep in mind that we said that I'm the one here. Keep in mind that I said that when water interacts with an H plus ion, it makes a covalent bond, and that's where you get your hydronium ion. It is hypothetically possible to do the opposite. Instead of taking a lone pair and turning it into a bonded pair, it is also possible to take a bonded pair and turn it into a lone pair. If you do that with a hydrogen as part of that covalent bond, you go from having a bonded hydrogen to an unbonded hydrogen ion or proton. So what we could say here is, I'm going to use a different color to make my point. Instead of using this lone pair to pick up an atom, we could take this lone pair, or this bonded pair, and turn it into a lone pair. And you guys have to help me with this. I think yeet is the word. I think if it just leaves. I would go. I'm not done yet, so I'll go at the end. I'll show myself out. But what can happen here is that whenever there is this bonded pair with a hydrogen, there's this potential to turn it into an H. But like I said, these H pluses don't really exist in solution by themselves. This process is facilitated by having another compound, another substance, another group of a molecule able to pick up this H plus. It really facilitates the whole process. This is where NH3 really shows that how it can function as a base. Because don't forget that ammonia, this nitrogen has a lone pair. And so what can happen is that these bonded electrons can become non-bonded electrons, and the hydrogen will get picked up by the ammonia. This means that our products will actually look like this. This is our ammonium ion, and what's left behind is OH, but don't forget that the electrons stayed with the oxygen, so this substance now has a negative charge. And by doing this, this chemical process creates the hydroxide that we were looking for. So it's weird that ammonia is a base not because it has the hydroxide, but ammonia is the base because it creates the hydroxide through a chemical process. The Regents calls this the alternate acid-base theory. I don't know why. I have my hypotheses. My best guess is that they didn't want to deal with more names and they just wanted to say like the Arrhenius theory and then the other theory. But I'm going to give you the name. It's two names. Brønsted-Lowry. Both of them were chemists. I can't remember which countries they came from. They're both European, 1800s, 1900s, long time ago. But this theory puts forth that acids and bases are the way they are, not because they create hydronium and hydroxide directly through their dissolution, but more that they will interact with other molecules that involve a transfer of protons. Acids are acids because they donate or give H plus to other molecules. And bases are bases because they accept H plus from other molecules. Some teachers like to give a mnemonic device to help clarify this for people who get confused. Let's go with dark red. The mnemonic device is bad. I mean, it's poor, but it's also bad. It's bad. Bases accept, acids donate. Bases accept, acids donate. That's the Brønsted-Lowry acid-base theory, or Regent says alternate acid-base theory. This theory, because it involves a chemical reaction, it gets away from saying this must be an acid and this must be a base because it's an acid and it's a base, and it gives a little bit more context to say, in this situation, this substance is an acid, and in this situation, this substance is a base. And I think this is probably the best way I can show it. Oh, sorry. We're going to go through... Sorry. I got ahead of myself. But because it's a chemical process and there's context, you can actually add another layer in looking at equilibrium. Many of these Brønsted-Lowry acid-base reactions will occur in equilibrium. For example, we have acetic acid in our top example. Acetic acid is, of course, going to be an acid. And we can kind of look at this because the substance goes from being HC2H3O2 to over here you have the substance in the form C2H3O2 minus. So this has lost an H plus. And the water goes from being H2O to H3O plus. This is gained an H plus. So that would make water, in this case, the base of the reaction because the acetic acid donated a proton to water. But because this is an equilibrium, we can kind of look at this in two ways. Not kind of, we have to look at this in two ways. So let me switch colors really quick. So if we were to just look at the reverse reaction, the H3O plus becomes H2O. Well, it lost. That makes in the reverse direction, H3O plus is an acid. And then C2H3O2 minus becomes HC2H3O2, so it gains an H plus. That would make this a base. So interestingly, in Brønsted-Lowry reactions, particularly the ones that are in equilibrium, in the forward direction, the substance that is acting as an acid actually acts as a base in the reverse direction. And this word, conjugate, is used to refer to the pair. So what we would say is C2H3O2 minus is the conjugate base of HC2H3O2. So the acid will react and become the conjugate base, and the base will react and become the conjugate acid. And so this term conjugate, they say conjugate acid-base pairs. And these pairs always differ by an H plus. So H2O and H3O plus are conjugate acid-base pairs where the acid has more H's. So this would be a base and a conjugate acid, or I guess if you wanted, you could call that the acid and the conjugate base. It's really that the two are a conjugate pair. As a way to show that you maybe know what's going on in case you want to see another example, I want you to take a minute, hit the pause button, everything's written here, look at the second reaction because everything has H's, everything has O's. I want to see if you can identify which one's the acid and the base on the left side and the acid and the base on the right side being the products. And I think I did left and right, or I should have did left. Anyway, hit the pause button, take a minute. All right, so looking at this, we've got the PO4 is really what you're going to latch onto to see what became what. I think these two substances are paired, and I think these two substances are paired. So going from H2PO4 to HPO42 minus, this would be the acid of the pair, and this would be the base. And going from HCO3 minus to H2CO3, that would have to be the base, and that would have to be the acid. Whenever you're given an acid-base reaction, there always has to be one of each on both sides of the equilibrium. You can't have two acids. They can't both donate to each other, because then overall nothing would happen. There's always a giver and an acceptor. There has to be. Period. The end. So let's make this a little bit weirder. I'm going to point out something. In this reaction, water acted as a base. In this reaction, water acted as an acid. So is water acidic, basic, neutral, both? It's very fortuitous that water is a kind of like a cornerstone of this planet and our life because it's got a lot of flexibility. When reacting HCl with water, it's a base. When reacting NH3 with water, it's an acid. What you could say is that water is an acid or a base when the context shows it. And that's why I like the Brønsted-Lowry acid-base theory. You can kind of look at it. It depends on what else is there. Now, the weird question is what happens when you just have a lot of water? Well, I suppose there's nothing wrong with one water acting as an acid and one water acting as a base. It's hypothetically possible. I'll tell you that it reacts in equilibrium. The first water acted as an acid, the second water acted as a base, and this totally happens. This means that in this water, there is both water, there's three things. There's waters, there's hydroniums, there's hydroxides. They're all there. Every time you drink water, you're drinking tons of both. Who knew? Now, water is not the only substance that does this. There are others that do this. I'm just citing one example. There's vocabulary that describes this. I guess I could say it. The word is amphoteric. It's a substance that can act as an acid or as a base as the situation dictates, as you see it happen chemically. So I wanted to put that out there. But this reaction is this is kind of the point of today's video. By looking at how acids and bases react with each other instead of how they exist absolutely, you can kind of come up with a framework whereby you can look at water acting as acid and base with itself, which really builds the cornerstone for aqueous chemistry and a number of other things. So just to sum things up, acids and bases can be defined by their chemical behavior. And the way to remember is that bases accept, acids donate. This is our Brønsted-Lowry theory, and I'm broken it down to so many letters. Bases be right. And then the last thing is that bases become conjugate acids, acids become conjugate bases, and those are frequently in equilibrium with each other, and they're always differing by an H+. Thanks for watching.